Okay, and we are rolling. The Mask Professor does the lecture of April the 22nd. Take 2. Hello, students and others. How nice you could drop by. Today we will be going further into Chapter 8, Statistical Intervals for a Single Sample. Let me arrange myself carefully here. I feel free to take off my mask now since I'm here all alone. As far as I know, I've been the only one in this room for weeks. All right, so we will pick up with slide number 7, where we can choose our sample size depending on how much error that we want to tolerate in our confidence interval. So our sample size for a specified error on the mean with the variance known, if x bar is used as an estimate of mu, we can be 100 times the quantity 1 minus alpha % confident that the error, absolute value of x bar minus mu, will not exceed a specified amount E when the sample size is n equals the quantity z alpha divided by 2 times the standard deviation divided by E. That quantity is squared. Wow, that seems like a pretty easy situation. Easy to calculate, of course. So, what the heck? Let's play with a couple of problems. Have to get the proper pen here. And let's make this a little bit larger, but not too large there. So let's do an example of choice of sample size. Let us say that we are given a circumstance where our standard deviation is equal to 2, a 95% confidence interval, forgot to put my percent sign, and we want an error equal to 1. Okay, so to refresh your memory from our previous lectures, 95% confidence interval, we would go, if we didn't know that right off, which actually I do because we use 95% all the time, our confidence interval percentage equals 1 minus alpha times 100%. Or, as they put it in the book, confidence interval percentage equals 100 times 1 minus alpha percent. All right, if you're going to be really super picky. All right, so what do I do with that? Well, what I want to do is find my alpha, which allows me to find my alpha divided by 2, which lets me find my z alpha divided by 2. So I substitute in 95% here equals 100 times the quantity 1 minus alpha percent. I divide both sides by 100%. Right? Because when we have an equation, that means we have to keep things equal. What we do to one side, we have to do to the other. Ow. All right. Doing this is going to move my decimal place over 2 places, so that becomes 0.95 equals 1 minus alpha. On my next step, I'm going to go 0.95 minus 1 equals 1 minus alpha minus 1. Okay, so that means my 1's drop out. This becomes a negative 0.05 equals negative alpha. I am then going to multiply both sides by -1, so we get alpha is equal to 0.05. Therefore, when I divide both sides by 2, I get 0.025 equals alpha divided by 2. All right, well, wasn't that an exciting calculation? All right, now I am going to take my z table and I'm going to say, where can I find the probability alpha divided by 2 equal to 0.025? All right, so I start looking here. Oh, where could it be? Where could it be? Well, of course, I really, as I said before, I already know where it is. All right, so here we have a row that starts with 0.023, ends with 0.028. You know what? I bet 0.025 is right in there. And I'm going to choose 0.024998 as being the closest one to 0.025, right? Because it's only 2 millionths off from that number. All right, so I come in here and I go ahead and now I've got my 0.024998, which we're going to call 0.025, close enough for the government job. And then I'm going to say, all right, I've got a negative 1.9, and I've got a negative 0.06. I add those together, and I get negative 1.96. Therefore, Z alpha divided by 2 is 1.96. All right, well, an exciting time was had by all. So, now, that implies Z alpha divided by 2 equals 1.96. Now, I am going to put down my formula N equals the quantity Z alpha divided by 2 times standard deviation divided by error, that quantity squared. Okay, not the best handwriting ever, but sorry, I seem to have injured my wrist somehow. All right, well now I have everything I need to work that equation, because we already said that we have a standard deviation of 2 and that we want an error of 1. All right, so equals 1.96 times 2 divided by 1 squared. Okay, well, I have to use Excel to figure that out, because I don't have a calculator here with me. So, 1.96 times 2, comma 2, right? I'm using the power function of Excel. Oh, I forgot divided by 1. Although, because it's dividing by 1, it won't make any difference. Okay, so that number N equals 15.37. Now, can we have 15.37 samples? No, you can't have 0.37 of a sample. Therefore, we have to round up to 16. All right, well, 16 is not too bad to as far as collecting numbers of samples goes. Unless it's like your samples are counting the number of teeth in lions or something similarly dangerous. All right, so that is not too bad at all. We can certainly deal with that. All right, but what would happen if we use exactly the same setup, except that except we wanted a 99% confidence interval. All right, so I'm going to use the same numbers except for 99%. So I'm given that my standard deviation is 2. I still want an error size of 1 and 99% confidence interval. All right, look, as you go along, you should start not having to do the first part, which is write down that our confidence interval percent equals 100 times the quantity 1 minus alpha percent. As time goes by, you'll start to see the trick and be able to just immediately go there. But for now, we'll keep doing it. All right, so 99% equals 100 times 1 minus alpha percent. I divide both sides by 100%. So that here I'm going to get 0.99, and over here I'm going to get 1 minus alpha. Then I subtract 1 from both sides. All right, so my 1's drop out. Over here, I'm going to get a negative 0.01 equals negative alpha. A negative 0.01, I should say. Of course, then I just multiply both sides by negative 1 to get 0.01 equals alpha. I just divide both those sides by 2 so that I get 0.005 equals alpha divided by 2. All right, so that is my probability of error on one side, since we're doing a two-sided equation. So, once again, I get my table. Right, and I get it here, and I look for where is 0.05, and then I start looking at which of these 0.05s is the closest to a true 0.05. And I am going to say that this number is the closest one. It's 0.004940, which is 60 millionths away, and this one is 0.005085, which is 85 millionths away. So that means that now I have a negative 2.5 for my row, a negative 0.08 for my column. And what we will do is we will then be able to take that and put that in our equation as our z alpha divided by 2. Now, I could put this down as our negative z alpha divided by 2 equals negative 2.58, and everything would still come out okay, because when n equals z alpha divided by 2 times standard deviation divided by error, right? A negative number squared is going to be a positive number. So it wouldn't matter if I put it in as a negative number, but just for grins, we're going to make it a positive number. All right, so n equals 2.58 times 2 divided by 1, that number squared. I lurch over here to my computer to use Excel. Equals power left parenthesis 2.58 times 2 divided by 1, comma, raised to the power of 2, right parenthesis, and I get 26.63. Now, Can we get 0.63 of a sample? Oh, hell no. So therefore, we round up to 27. So therefore, we would want 27 samples in this case to get an accurate reading where we know that the error is 1 or less. Now, one thing you may have noticed, let me see if I can put these side by side. When we do a 99% confidence interval, we need 27 samples. Whereas when we do of 95%, we only need 16 samples, right? The more percentage accurate we want to be, the more samples we have to have. Okay, all calculations that I do today, I will post on Moodle so that you can have those there in your hot little hands. Now, I want to do one more calculation on sample size. All right, in this case, I'm going to take some of the same facts that we used before. So, given that our standard deviation equals 2, excuse me, I need to change that. Instead, let's make our standard deviation size 3. Our error equal to 0.5. And for a 95% confidence interval, which of course implies Z alpha divided by 2 equals 1.96. All right, once again, our sample size equation, N equals the quantity Z alpha divided by 2 times standard deviation divided by error, that quantity raised to the second power. Right? Well, we already have all of our numbers. N equals 1.96 times 3. Oh, and E is 0.5 squared. Therefore, N is equals power 1.96 times 3 divided by 0.5, comma, 2, right parenthesis, equals 138.30. Holy tuxedos, that is giant size, right? But it's because of making our error so small. And of course, we would go ahead and simplify that to be 139. We still can't get 0.30 of a sample. All right, well, what would have happened if we had just used an error of 1 like we did before? That would be n equals z alpha divided by 2 times standard deviation divided by e, that quantity squared, equals equals 1.96 times 3 divided by 1 squared, which would mean that n would be equals power 1.96 times 3 divided by 1 raised to the second power, right parenthesis, which would be a 34.57 or 35 samples. All right, so you can see what a difference it makes. You would have to have 4 times as many samples for just going half the size of the error. So we want to choose our error size very carefully. All right, well, meanwhile, back at the ranch, as they used to say on cowboy shows when I was a kid, all right, so now we've seen how we calculate a sample size for a specific error. And here we have an example. They can extend the example of example 8.1 and say, consider the CVN test described in example 8.1. Determine how many specimens must be tested to ensure that the 95% confidence interval on mu for A238 steel cut at 60 degrees centigrade has a length of at most 1 joule. In other words, they're trying to limit the sample size, the confidence interval length by how much error they want. Okay, so they say the bound on error in estimation of E is 1/2 of the length of the confidence interval. Use equation 8.6 to determine N with E equals 0.5, standard deviation equals 1 joule, and Z alpha divided by 2 equal to 1.96. We all know that that is for a 95% confidence interval. Bloody hell. I hope I don't keep tripping over my tongue. I don't want to have to start on take 3 of this lecture. All right, so n equals the quantity z alpha divided by 2 times standard deviation divided by e. That quantity is squared. We substitute in our numbers. 1.96 times 1 divided by 0.5. That quantity squared is 15.37. All right, so because, again, our sample size has to be an integer number, we round up to n equals 16. Okay, pretty easy peasy. Now, when you were introduced to confidence intervals, you were introduced as though it would always be a two-sided confidence interval. But we often need to deal with a situation where there is a one-sided confidence interval. So a one-sided confidence bound on the mean with the variance known. Variance known is very important. When we get to variance unknown, you're going to see why. A 100 times the quantity 1 minus alpha percent upper confidence bound for mu is less than or equal to x bar plus z alpha. You'll notice it's just z alpha, not z alpha divided by 2, times standard deviation divided by the square root of n. And a 100 times the quantity 1 minus alpha percent lower confidence bound for mu is x bar minus z alpha times the standard deviation divided by the square root of n is less than or equal to mu. Okay, so when we don't want our mean to exceed a certain amount, we use our upper confidence bound. When our mean has to be at least a certain amount, we use our lower confidence bound. All right, so let's extend example 8.1 a little bit more and do it as a one-sided confidence bound. All right, so the same data for impact testing from example 8.1 are used to construct a lower one-sided confidence interval for the mean impact energy. We have to remember x bar equals 64.46, that our standard deviation equals 1 joule, and that our sample size is 10. So a lower confidence bound for mu, they forgot mu here, is x bar minus z alpha times standard deviation divided by the square root of n. Our sample size is less than or equal to mu. We substitute in 64.46 minus z alpha, in this case 1.64, times 1 divided by square root of 10, less than or equal to mu. And we get that 63.94 is less than or equal to mu. Okay, so in this case, we want the impact energy to be above a certain level. And we're hoping that 63.94 joules is the right number for that. All right, so you may be saying to yourself, wait a minute, a 95% confidence interval for a one-sided confidence interval. How does that work? I'm glad you asked that question. Or at least I'm assuming you're asking that question. All right, so let's remember that our confidence interval percentage equals 100 times 1 minus alpha percent. In this case, we're only going for alpha. We're not worried about alpha divided by 2. So that means that 95% equals 100 times 1 minus alpha percent. Again, as always, I divide through both sides by 100%. Oh, and of course you're getting none of this because I hadn't moved the head of the cube view. Very embarrassing on my part. Okay, so let me go through it again. Our confidence interval percentage equals 100 times the quantity, 1 minus alpha percent. I substitute in my 95% for my confidence interval percentage, confidence level. That's equal to 100 times the quantity 1 minus alpha percent. Then I divide both sides by 100%. So that means I'm going to move my decimal place over 2 places here and say this is 0.05. And over here, 100 divided by 100 is 1. And I'm going to say percent divided by percent is 1. So it comes out to be 1 minus alpha. Now I am going to subtract 1 from both sides. So 0.05, or excuse me, that should be 0. God damn it. All right, once more under the breach, dear friends. %, confidence interval, but with a one-sided confidence bound. We know our formula is confidence interval percentage equals 100 times 1 minus alpha percent. We substitute in 95% equals 100 times 1, the quantity 1 minus alpha percent. We divide both sides by 100%. And here we get 0.95. And over here we get 1 minus alpha. On both sides of the equation, I subtract 1. That means 1 minus 1 is 0, and 0.95 minus 1 is negative 0.05 equals negative alpha. I go ahead and multiply through by negative 1 on both sides to get 0.05 equals alpha. Oy vey. All right. Therefore, what is Z alpha? Well, I get my famous table, so famous, so table-y, and I am going to search for where is the number, the probability that is the closest to my 0.05. And that is right here at the negative 1.6 row, right? We could see along here 0.048, that's getting close. 0.049471, that's really close. And 0.050503. Oh, wait, 0.050503. Okay, right. There we are. So that means these two numbers are incredibly close to my 0.05. They are so close that I could choose either one of them and feel pretty confident in the results. Or, as we often do with this particular situation, sometimes we split the difference. Right? So, right here, I've got negative 1.6, negative 0.04, right? So that makes this, that would mean that we're choosing this number, right? Which would be a negative 1.64. We could also choose a negative 1.65, right? Negative 1.6 plus negative 0.05. Or sometimes we go right in the middle and we call it a negative 1.645. All right, so in the book, as you saw in example 8.3, they chose 1.46. But I'm going to say that is super close to 1.65. Excuse me, 1.64, not the other way around. Very close to 1.65. Some would say even closer to 1.645. If we have a problem like this in class, I am going to be okay if you choose 1.64. I'm going to be okay if you choose 1.65. And I'm going to be okay if you choose 1.645. Okay? It's not going to affect the results enough to get myself all in a lather about it. All right. So, therefore, that is how we would get our Z alpha for a one-sided confidence bound at 95%. What about a 99% confidence interval, one-sided confidence bound? All right, we're going to use the same method we've been using all along. Our confidence interval percent equals 100 times the quantity 1 minus alpha percent. In this case, we're going to put 99% equals 100 times the quantity 1 minus alpha percent. As usual, we're going to divide through by 100%. So that we get 0.99 equals 1 minus alpha. I'm going to subtract 1 from both sides. So my 1's drop out. I get a negative 0.01 on my left side and a negative alpha on the right, which I multiply both sides by negative 1, making it 0.01 equals alpha. So what is my Z alpha equal to? Well, let's take a look here. We know that if it was two-sided, it would be 2.58. But we are looking for 0.01 as our probability. And it looks like, am I here? This actually looks like the better choice of row. Okay, so the negative 2.3, I come over here, 0.0096, that's getting close. 0.0099, that's even closer. And 0.010170, that's pretty close too. I'm going to choose this number as being closer to what we want. Okay, so I'm going to kick up so that we can actually read what the numbers are across the top. I'm going to place my piece of paper so that I've got negative 2.3 plus negative 0.03. Or in other words, um, my z number is going to be 2.33. Now, often that is interpreted as 2.32. Okay, but again, I'm not going to get all upset if you make a slight error in this regard. All right, so my Z alpha is 2.33, but again, call it 2.32, I'm not going to worry. All right. Now, let's do a problem or two from our fifth edition book. Why not our sixth edition, since the book that you have is the seventh? Because someone has stolen my book. But I still have my fifth edition book. All right, so let us look at all right, let's do fifth edition problem 810. Past experience has indicated that the breaking strength of yarn used in manufacturing drapery material is normally distributed and that standard deviation equals 2 psi. Okay, so standard deviation equals 2 psi. A random sample of 9 specimens is tested, so n equals 9. And the average breaking strength is found to be 98 psi. All right, so x bar equals 98 psi. All right, so find a 95% confidence interval. All right, so we want our breaking strength to be above a certain value. So let's do a lower bound one-sided confidence interval. All right, so of course that is going to be of the form x bar equals, minus z alpha times standard deviation divided by square root of n is less than or equal to mu. All right, so x bar is 98 psi. minus, now Z alpha for a 95% one-sided confidence interval, we already did the calculation, and that is 1.645 or 1.64 or 1.65. So I'm going to call that 1.64 to keep the math somewhat simple. Our standard deviation is 2 psi. Notice that both terms of our equation are in pounds per square inch. Divided by our sample size of 9, the square root thereof. All right, and that is less than or equal to mu. All right. Well, it would be pointless for me to go ahead and do the calculations by hand there in front of you. So I slip over here and I say that 96.90 psi is less than or equal to mu. All right, well that is great if we need an average breaking strength of 95 or higher, even 96 or higher. All right, well, fantastic. All right, what if we want to be 99% sure on that same calculation? So then our given is still standard deviation equals 2 psi. Our sample size is still 9. Our x bar is still equal to 98 psi. And you remember that our Z alpha equals 2.33 in that situation. Oh, man. All right, so our equation is still x bar minus Z alpha times standard deviation divided by square root of sample size less than or equal to mu. So that is 98 psi minus 2.33 times 2 psi divided by square root of 9 less than or equal to mu. All right, so I slip over here, equals 98 minus 2.33 times 2 divided by square root of 9 and that becomes 96.45 psi. So if our standard is still that mu has to be at 95 psi or higher, we're good. All right, so let us do, from the 5th edition again, problem 8-13. The life in hours of a 75-watt light bulb is known to be normally distributed with standard deviation equals 25 hours. All right, so our standard deviation equals 25 hours. A random sample of 20 bulbs, n equals 20, has a mean life of x bar equals 1,014 hours. All right, so x bar equals 1,014 hours. Construct a 95% lower confidence bound on the mean life. All right, so we want 95% confidence interval, and on the lower bound. All right, so that means our formula is still x bar minus z alpha times standard deviation divided by square root of n less than or equal to mu. So x bar is 1,014 hours minus 95% one-sided confidence interval means that z alpha is equal to 1.64. Damn it, I'm putting 645. I don't care whose ox is gored. Our standard deviation is 25 hours divided by the square root of our sample size at 20 hours less than or equal to mu. Oh, this should be in hours. All right. Once more, slipping over square root of 20 that implies that our bulbs will last that 1,004.8 hours is less than or equal to mu. Okay. Well, what if Oh, that was a great move on my part. What if instead of worrying that they would last a certain, at least a certain amount of time, we didn't want them to last more than a certain amount of time? In which case we would do an upper bound test. So that would mean mu less than or equal to x bar minus z alpha times standard deviation divided by square root of n. Excuse me, plus z alpha times standard deviation divided by square root of n. Our mu is less than or equal then to 1,014 hours plus 1.645 times 25 hours for our standard deviation divided by the square root of 20. Okay, well, an exciting time. So I slip over here, I do the calculation, and it is 1,023.2 hours. So we know that mu is less than 1,023.2 hours. Okay, not bad at all. All right. Right, I'll show you my worksheet here on Excel. I did not label everything the way I would have if I was going to, the way I would if I was going to give you this. What I am going to do is I am going to scan all of these problems that I did today and put them on Moodle for you to use. And that will be it for today. I will be in contact with you, and when the fields are white with daisies, we'll meet again. Thank you very much.